Thank you very much. Good evening, everyone. At first, I would like to thank you all for your patience, and I would like to apologize for making you all worry. It seems that you have to eat before presentation. Thank you for your patience, and special thanks to Natalia for the help. So now, I would like to present to you our recent work in measurements in QFT in a relativistic setting. Though I will be a bit quick in the introduction because some of you, to gain time. Yes, thank you very much. So I am going to show you how we move from scalar field models to more realistic scenarios, treating detection as a space-time process. So we applied this framework to photons, Dirac, and composite particles, but in this presentation I will show you neutrinos. Well, our goal is mainly to make a bridge between QFT measurements and real experiments. So the basic question and the basic problem that motivated us to this work is that in quantum mechanics we deal with measurements that are associated with an instant moment, but that's really problematic in a relativistic setting. So since in QFT measurements, we do not have a measurement in an instant moment because physical events are spread through space-time, and that's a real problem we have to answer. So, in the standard framework, measurements are manifestly compatible with relativity in the sense that the detector is ideal and instant. But the truth is that the detector is a physical system that has a specific temporal window and a finite spatial resolution, and moreover interacts with the field, and that's very important. But on the other hand, QFT only provides probabilities for observables. So there is a gap because it cannot directly describe the detection of an event. So in order to be more accurate in our description of a measurement, we have to include the detection in the formalism. Therefore, in our approach, we use probabilities that are expressed through correlation functions of the field combined with the characteristics of the detection. To achieve that, because the key idea was that since that in other measurements, in other approaches, the measurement are really focused on scalar fields, we extend this to more realistic scenarios, and in order to achieve that, we use the framework of the quantum temporal probabilities, in which we treat time as a random macroscopic variable. And that means that instead of asking what times happen something, we ask at what time the detector click. So we move from the measurements now corresponds to physical events, and probabilities are structured through correlation functions. And as I said before, we do not describe just the system, but the detector and the system. So as a consequence, everything boils down to how the field couples to the detector, and we express this interaction through this coupling term. As you see, we have field operator C, which is a local composite operator that describes the quantum structure of the field and encodes space-time and integral degrees of freedom. And on the other hand, we have the detector current J, which lives in the detector's Hilbert space and describes how the detector couples to the field. So the detection probability takes this form, this space-time integral over 2 points. The first one describes the correlation functions of the field, the structure of the field, in fact. But the second one is the detector response kernel. And this one is really important because he encodes all the setup resolution, the coupling, the sensitivity, and all the information about the measurement is in this one. Another crucial ingredient in this one is this P operator, which is positive and self-adjoint and dynamically stable, and his role is to ensure us that the measurement outcome is going to be well defined and does not evolve under the detector's free dynamics, characteristic of free dynamics. Yes, let me move. Livon. So, the picture has been changed radically since now the measurements we do not have collapses in an instant moment. So that means that we do not measure ideal measurements, and we do not have physical events that are spread through space-time, because now the detector is a protagonist as well. So what we did was to apply this framework to different physical patterns, photons, as I said, Dirac and composite, in all cases are unified under the time of arrival probabilities. So let me now turn in a specific example, which is the detection of the Dirac field. And this detection is clearly not a scalar process, because it's sensitive to spin and directional structure of the and so all information about the spin and the directions and the field apparatus interaction must all incorporated. So in this case the detector couples to a local current, the detect current, which is built from the field operators. And as a result, the probability here is no longer purely translational. It now depends on the matrix Z, which encodes how the spin enters the description. So we are led to this operator Z. All information about the structure of the interaction and the spin dependence, everything is encoded here. He does all the work. It does all the work. And as you see, it factorizes into two parts. The first one indicates how the detector probes the system, when and where is active, and what kind of currents are detected, while the second one it captures the intrinsic dynamic of the Dirac field, and and the spin dependence, of course, and in particular, it captures how a free Dirac particle can exchange for momentum independently of whether it is being observed. In order to derive time of arrival probabilities, we found this matrix, this spin-dependent localization matrix S, which is constructed by the kernel Z after diagonalizing it in terms of its eigenvectors and eigenvalues. Its eigenvalues encodes how strongly each spin component contributes, while the eigenvectors encodes the spin directions that are selected by the detector. So the time of arrival probability has the same structure as before, but now it depends on this matrix S to, and it's clear that it's spin dependent. The spin dependence has entered the description. So to illustrate this, I present you this plot showing the time of arrival distribution in the ultra-relativistic limit for two different spin states, 1.5 and -1.5. And for this presentation, I chose a symmetric response kernel. And any difference between the spin channels is due to the structure of the kernel. It's technical. So the key point here is that even in an ultra-relativistic limit, the detector is still sensitive on spin. So what do we learn from this is that detection is not a purely scalar notion, and leads us, if we have in massive relativistic particles this dependence on spin and how the spin couples to the detector, then it leads us to qualitatively different detection patterns. So another one is photons. Here the structure simplifies, but the same framework applies. And it splits into two parts. The first one encodes intensity, while the second one is important because it physically represents the oscillatory phase-sensitive contribution of the field. So when we include temporal coarse graining, it's strongly suppressed, and we have a classical-like behavior. And in the appropriate limit, in a far-field limit, we have the classical photodetection. And finally, neutrinos. In the case of neutrinos, again, the detection affects what we observe, namely the oscillation pattern, because oscillations here are emerged from amplitudes, from detection amplitudes, and that has an immediate consequence in neutrinos, since coherence is now again on the hand of the detector. So I'm gonna be as quick as possible because. So to conclude, we found that in relativistic QFT measurements, detection is not something purely scalar. So what I want to say is that it depends on the detector, and it depends on the underlying structure of the interaction. So we found that it affects localization in Dirac and rigorously defines oscillation in neutrinos, and we have the Q contribution on photons. So in order to have a consistent measurement, we have to keep in mind that the notion of localization is not an intrinsic property, but something that emerges through detection. And in this sense, what we call a particle emerges through detection. So thank you all again.
Thank you. So we have time for a few questions. Any questions?
Thank you very much for the very interesting talk.
Thank you.
So, is it straightforward to generalize to higher spins, even higher? Well, no higher spin particles, elementary particles, have been detected yet, but is it easy to generalize to higher spins?
It's not something that I have worked on, but I suppose it is from a quick response.
Is something obviously clearly wrong with the graviton?
It's not my area.
Okay. Yeah. Okay.
I'm sorry.
Yes.
I can answer that question to
Okay,
you.
yeah,
It's
sure.
not my area. Thank you.
Thank you very much. Yeah.
We have time for one more question. Okay, so just let me ask you one quick question. Yes. So you're modeling detection of a particle, you're using this smeared fields essentially. And when you think about one detection of particle, and can I think of the next detection of the same particle and ask about the speed of it, if it's still respecting being smaller than the speed of light? Because when you think about Newton-Wigner localization, for instance, we have these issues that you can propagate super luminous speeds. Can there be a similar feature here, or it does not happen in your model?
Well, let me tell you, in our model, we incorporate we do give a big weight on the detector. So we apply this from this perspective. So from this perspective, everything can be detectable, if that's what you ask me.
Yeah, and if there can be some propagation of the particle that is faster than light.
We haven't shown something like this.
Okay.
Okay.
Thank you.
Thank you.
Okay, let's thank again.